the module called full subtractor. It takes three inputs, A in, B in, and borrow in, and its purpose is to compute A in minus B in minus borrow in, right? And it produces the difference output and the borrow output. And we did that Karnaugh map and figured out what the difference output is and what the borrow output is, right? And we wrote assign statements to sort of output, difference output, and borrow output. Then using the full adder, the full subtractor, we tried building a 4-bit subtractor. So here x and y are 4-bit inputs, okay, and the borrow input is a 1-bit input, and we get a 4-bit difference and a 1-bit borrow output. So we made use of 4 subtractors, okay, and they sort of act in a ripple carry manner. So this is the 0th stage. There are 4 stages, and we label them 0, 1, 2, 3. In the 0th stage, we are subtracting y0 from x0, and any incoming borrow we subtract as well. So that will give us d0, and the borrow which we call as temp1, and that goes as an input to the next stage, okay. And then similarly, temp2 is a borrow from this stage, it goes as input to the fs2. Temp3 comes out as the borrow output, that is sent as an input to fs3. And what we get as borrow from the last stage is actually the final borrow, right? And we decided to write a test bench, okay, called sub4 test. And here we declared A and B as 4-bit registers and the borrow as a 1-bit register. And diff is a 4-bit wire and R out is a 4-bit wire. And remember how we instantiate the subtractor. So subtractor 4-bit, which we wrote earlier, right? So this is our subtractor 4-bit. And we are creating an instance of it here. And the instance name we gave was sub4 instance. You can give any name you want. And remember how we are binding. The X input is bound to A. Register A is sending the input to X. The register B is sending the input to Y. And Rin is sending the input to Rin. And difference is coming out from the D output. And the borrow is coming out of the R out output. And I had mentioned to you that the order here is not important, right? Because you are explicitly binding. Okay? You are not depending on the order of the inputs and outputs. So frankly, it doesn't matter, right? See, in the industrial situation, the names will not be simple like A, B, C, etc. So sometimes the names can be very long, right? Because the module may be, receiving inputs, right? So it may be a very complex name, right? And as a result, when we write, we sometimes write one in every line. Okay? See, it's better to organize the information correctly, right? Even the way you write the code matters, right? So if you write something like this, you can see it is a little bit more readable, right? So the intention is not just to get something working, but also make sure that you can maintain it, right? See, this test bench, though we have written it now, maybe we may have to revisit it later, okay, and we may have to fix a few things, right? So at that time, it is better to write it in a way that it is easy to read, right? Now we are writing a in the test bench. What are we doing? We have decided to exhaustively test it. Okay. So how do we do it exhaustively? We are sort of applying. We have declared integers I, j, k, and we take I from 0 to 15, okay, and j from 0 to 15, and k from 0 to 1. And in this loop, inner loop, what we are doing is we are assigning a to I, b to j, and r into k. So in other words, a will go from 0 to 15, b will go from 0 to 15, rn will go from 0 to 1. So the number of test cases will be 15, I'm sorry, 16 times 16 times 2. So this is about 512 tests. Okay. Since the 512 is not such a large number, so we may be able to survive. Okay. But if this becomes a 8-bit subtractor or a 16-bit subtractor, you will realize that it is not going to be that easy, right? And here is where I think we were facing some difficulties. We were trying to output, you know, see when we apply the inputs, we wait for a 1 unit time, right, for the circuit to respond. Okay, immediately we should not print the output. And when we do so,
Excuse me, sir.
yes,
Sir, the screen is not visible, sir.
oh my goodness, okay, nobody told me. Just a minute. Okay, sorry. So I'm sorry. Are you able to see?
Yes, now it's visible, sir.
Okay. See, I'm not able to see your chat. Okay, so you have to speak up. If there is a emergency like this, you have to speak up. Otherwise, I will not be able to. Uh, I was trying to show you this code. Okay, looks like people did not see. So we started by writing the full subtractor, right? And then we used it to build a 4-bit subtractor, and then we wrote a test bench for the 4-bit subtractor, right? So as I was explaining to you, we are exhaustively testing the 4-bit subtractor. So the 4-bit subtractor takes inputs x and y, which are 4-bit, and the borrow, which is 1 bit. So totally there are 9 inputs, and as a result there can be 2 to the power 9 tests, right? So there are 512 tests, right? And we apply the test here and then wait for the signal to propagate, and then finally we display the output, right? And we notice this behavior, right? So what is happening is 1 minute, huh? 1 second. Okay, sorry. So what we are trying to do here is we are saying the when we apply this input A, okay, and A minus B, right, minus the input, that is the borrow input. Okay, A minus B minus borrow should be equal to, and how did we calculate this output? See, we have got a 5-bit output. Okay, if you look at difference and the borrow as a 5-bit number, right? So let me illustrate that here. Suppose the input is 0111, okay, which means 7, and the output is I'm sorry, the other input is 0 1000, and the last input is 0, the borrow input is 1. So we essentially are calculating 7 minus 8 minus 1, right? So the circuit will produce 1 minus 0 minus 1. So it will produce 0. Okay. And as a result, there will be no borrow. 1 minus 0 minus 1, there is no borrow. So then it will produce 1 minus 0 is 1. Then 1 minus 0 is 1. Okay. And 0 minus 1 will be 1. Okay. And borrow will be 1. Okay. So this is the output it has produced. Okay. So what really has happened here is this is a negative number. Okay. This is a negative number. So you may remember that in 2's complement arithmetic, if in the 2's complement representation of numbers, if the most significant bit is 1, then we take it as a negative number. Okay. So the actual value of this number, okay, if you treat it as a negative number, is convert this into its 2's complement. So what will happen? We first invert all the bits. So 0 0 0 0 1, and then add 1. So 2's complement is nothing but 1's complement plus 1. So we'll get minus 2. Okay. So 7 minus 8 minus 1 is actually minus 2. Okay. So another way to write the same thing will be, so you treat this as an unsigned number if you want. This 1110, right? We could treat this as a 4-bit unsigned number. So that will make it 14. Okay. 1110 is 14. But you can, because it's a negative number, we can sort of have a negative weight of minus 16 for this. Okay. So minus 16 plus 14 is also minus 2. So it's up to you how you want to do this. So I had given this method, right? So I take the output uh, R out and attach a weight of minus 16 and then add 16. Okay, that is how I was trying to do, right? But unfortunately, what was happening was the negative numbers were being displayed like this. Okay, so what we have to do now is see when you do minus 16 times R out plus difference, right? Um, Let us try declaring this as a signed number. Okay, dollar signed I think is there. Okay, let us try that. Okay, so that might fix the problem. I'm not very sure. Okay, that looks like fixes the problem. So when you write dollar signed, that is a built-in function. Okay, so that helps me to fix the problem. Right? Can you see? Now things are looking okay. Okay. So 11 minus 14 is minus 3. 11 minus 14 is minus 3, etc. So dollar signed is a built-in function in your Verilog, right? Uh, so these are called system tasks. Okay, these are called system tasks. And here is one such system task which helps me to print this as a negative number. Okay, when you say dollar sign and give this large number that it obtained, right? Let me see, look at this. See, if I don't, treat it as a negative number, what has really happened is, see, because I'm computing this here, right? When I write minus 16 times RO plus difference, internally it will keep a 32-bit number. Okay, internally it will use a 32-bit representation for this guy, and it will pad additional ones. Okay, so there will be about 32 bits there. So 1, 2, 3, 4, 5, 6, 7. I think I have written too many. Okay, so unfortunately it was printing this as the positive value. Okay, but when you write, when you tell that guy that this is actually a signed number, then it realizes that actually it's a negative number and calculates it correctly. Okay, is that clear to everybody? Any doubts? Any doubts? Let me look at the chat in case anybody is having any problem. Oh, the volume is very low. Are you able to hear me correctly? Oh, somebody asked me why did I do minus 16? Okay. The reason is, let me show you. See, I am trying to take a 4-bit number, right? And I am subtracting another 4-bit number and a borrow. Okay. That may result in another borrow. So in this case, that actually happens. Okay. See, when I subtract 1 minus 0 minus 1, I get 0. Right. Then again 1 minus 0 gives me 1. 1 minus 0 gives me 1. 0 minus 1 gives me 1 with a borrow. Okay. So when I see, when you add a two 4-bit numbers, you get a 5-bit number, right? In the same way, when you subtract one 4-bit number from another and a borrow, the result may be in 5 bits. Okay? And if there is a borrow, it means it's a negative number. Okay? So you may be able to understand if I give you addition as an example. See, if I have 0, 1, 1, 1, to that if I am adding, let us say 1011, okay? What is 0111? It is 7. What is 1011? I believe it is 11. Okay? So the adder will generate 1 plus 1. Let us assume that the carry is also 1. Okay? So the last stage will generate 1 plus 1 plus 1. Sum is 1, carry is 1. Then 1 plus 1 plus 1, sum is 1, carry is 1. Then 1 plus 1 plus 0, sum is 0, carry is 1. Then 1 plus 0 plus 1, sum is 0, carry is 1. Okay? So we got 10011 as output. Okay? See, you should not look at it as only the last 4 bits and declare the answer as 3. The output carry has a weight of plus 16 in an adder. Remember, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So this has a weight of 2 to the power 4 or 16. So totally the answer is 16 plus 3 is 19. The answer is 9. And whereas when you are doing subtraction, the borrow has a weight of minus 16. Okay. So that is the reason I have added minus 16. Is that clear to you? Did it make sense? Okay. All right. So another thing we can do is, see, there may be a lot of display like this, right? So a verification engineer, really it will be too much if that fellow has to go through this whole input output and verify one individually one by one, right? So what may be worth it is, we know what the value is, right? See, we, this is the value given by the circuit. This diff and R out are what the circuit is computing, but we can compute it ourselves also directly. Okay, what is the actual difference? It is A minus B minus RA. That is output, right? So we can also try to display that side by side. So I'm going to display these two side by side and let us see what happens. Sometimes it takes a long time. I don't know what I did. I don't think there is anything wrong here. Just a minute. I have not used this JDoodle before. Maybe we'll use speed link. So here, let us try this guy. So you can see that it has produced output. I think that server for the tutorials point has some problem. Okay. So you can see that these are the outputs and they are sort of matching. Okay. Whether you directly calculate the output or whether you do it through the circuit. Okay. That is what we were looking for. Okay. So what you could do is you could say something like this. If dollar sign of a minus b minus rn is not equal to dollar sign of minus 16 times r out plus diff, right? Then you can say dollar display um, so this is an error case. So some error was there. So now if you run this guy, right? So I have put a condition. I expect these two to be same. And if they are not same, I will say this case failed. Wait a minute. Right? What did I do? Earlier they were both same, no? They are same 4 4. No, there are cases where it differs. So there is a case where it's 10 and this is minus 6. So we do have some problem. Okay. So there are some cases where there is a problem. See 15 minus 3, our answer is minus 4. Why is that? So 15 minus 3, we should have got so 15 minus 3, let us do. 15 is 1111 minus 3. Okay. And I think what is the answer here? 15 minus 3 minus 0. So carry is 0. So the answer would be 1 minus 1 is 0. Then 1 minus 1 is 0. 1 minus 1 is 1. And then 1 minus 0 is 1. So this is 12, right? 15 minus 3 is 12. Why am I getting 4 here? The borrow should be 0, right? There is no borrow. So I'm getting a borrow. So that means there is a bug, guys. There is a bug in my this logic possibly. So we have to verify. Okay, so we actually found a bug. You understand? So 15 minus 3 is 12, but I am getting minus 4 because I have looks like the borrow is wrong. The last stage, the borrow is incorrect. So just check where it could be. X2, X3, D0, temp1, D0, D1, D2, D3, temp1, temp2, temp3 R out, temp1, temp2, temp3 R in. And this also we have to check very carefully. So we have assumed all along that this is correct. For a minute, let us use a different method. The full subtractor, right? Let us use a maybe behavioral code or something like that. Always at A in, B in, borrow in. What we want is borrow out and diff out is equal to A in minus B in minus borrow in. Okay. So this is behavioral code. We are not explaining how the circuit will get this. Okay. We are going to leave it to the Verilog compilers, right? The synthesis tools. So now let us see. Now it should not give a mismatch. So this should be output. So we should say output reg here because we have declared this as a, we are assigning to it, right? So we should declare it as a reg. Okay. So 15 minus 2 is 13, but we still have a few cases. So it's always at 16 problem. Okay. So here let us verify which is the first one, which is the second one. The first one is what our program is generating, I think, right? That is what the first program is doing. I think the problem is in the verification. See, this is coming out to be wrong. This A minus B minus Rn is coming out to be wrong. Okay. So I believe the problem is not in the design, but in the verification code. That means we are comparing these two, right? A, B, R in. See the first one which I have written here, right? This is computed, was not same as percentage which was expected. Okay. So you will realize that the problem is with the expected. When we write signed of A minus B minus R in, that is where the problem seems to be. So this illustrates that sometimes the design is all right, but the verification has a bug. So what could be the reason why this is not working? A minus B minus R in. A is taken to be a, how many bits is A? A is 4 bit, B is also 4 bit, and Rn is 1 bit. I think in the second one it is not expecting me to put that. Okay, so now it's okay. Can you see both of them are matching now? Okay. Oh no, there is still a problem. Minus 900. So how do I actually do this, guys? See, this one we figured out by putting dollar sign. But this guy, A minus B minus R in, is not working correctly. What could be the reason? Let us see if this works. A minus B minus R in. Any ideas, bright ideas? Let me see if anybody is giving me ideas on chat. Input or out? No, no. Input and output should not be made 5 bits, man. Tejaswini. That is not correct. Second output is 4-bit binary, but you have displayed it using signed keyword. So that MSB is acting as a sign bit, so 110 is showing as minus 4. Which one, man? Let us see. And you know what? Another funny thing has happened here. Can you see? See, there are places where they are identical, right? See, 13, 13 is same as 13, but it is still saying they are not same. Okay, A minus B minus R in. See, A is 4 bit, B is 4 bit, and R in is 1 bit. When I write an expression like that, I think it will. How will it do it? Let us do one thing. We had a result or something like that, right? So let us try that. Result equals A minus B minus Rn. Okay, and the result is an integer. So let us see if this changes things. See, this worked. So when I was trying to do a minus b minus r in directly, right? Then I don't know how this guy is going to calculate, in how many bits it's going to calculate. But here I have declared integer as a result. So when I did this, looks like there was no problem. Okay. So sometimes, your verification code also can, be incorrect. So we should be careful. So the learning for us in this exercise was that if we find a bug, right, we should verify that the verification is okay. Okay. But sometimes, we may have, sort of written some. So what is the other thing that we learned here? See, writing this kind of if statements is very helpful because then, only errors will come. So you imagine that we were testing a very large circuit, right? If you start printing everything, right, then it is very difficult to debug. It's very difficult to understand what is going on, right? So try to minimize the output. Okay, when you want to debug a circuit or when you want to find out what is wrong with it, if at all anything, then the output should not be overwhelmingly. Then we will not be able to figure it out. Okay, so that is another. Is that clear to everybody? Did I make sense? No, now all the calculations are correct. See, the problem was not in the circuit per se, the problem was in the verification. See, we wrote the compare statement, right? See, I'll tell you once again. Okay. See, how do you verify? Sometimes in the exam, right, you get some answer, right, by following a certain method. And your teachers would have told you always verify your answer, right? One way to verify the answer is just do the same problem again using the same method, right? But there you are likely to make a mistake again, right? But if you have an alternate way, if you have a second method that you can use and both of them produce the same answer, then the chances are that you are there is no problem, right? That is what we are trying to do here. Okay, is that clear to you? See, okay, so Rajesh Kumar is saying it's clear to him. So this percentage d that I have written as computed, that is the circuit's output. If you prefer, I can show everything in binary. Okay. That way you'll also understand, right? You could see we are trying to write in decimal because we want to treat the numbers as decimal numbers. Okay, after all, they are 4-bit numbers and they are decimal numbers. But if you want, you can also print the same thing in binary and figure it out. Okay, so I am okay with both. Is that clear? Did I make sense to everybody? Jaivik Patel is saying yes. Dave, is it still like not clear? Okay. All right. So let us do one more exercise, which I may have last time I may have asked you to do it yourself. Right? Oh, now this answer has come. Okay. And see, this produced a very different answer. Huh? See, here the problem was not there. Okay, this guy has see compilers also change. Huh? I mean, the outputs of the compilers are slightly different. See, this compiler seems to have produced identical answers in both. Okay, so I did not have to do that result thing here. Okay, so there is a difference. You understood, no? So even the from one compiler to another, there may be slight variations. Okay, so that's another learning for you. Okay, so let me send this to you guys. Chat, but I'm not sure whether the whole thing will go. So what I'll have to do is I'll have to do it in pieces. So first I'll send you the test program. See, okay. So what I just sent you is the test program. I don't know why it is coming like that. It is horribly, all the lines are mixed up. Okay. The other one is this guy over here, from here to here. Okay. Hopefully you will be able to see it properly. Is that okay? All right. So let us do another exercise. Okay. This time, let us write a circuit which is both. It's going to do add or subtract. Okay. So let us write a module which is a full adder or subtractor. So again, the inputs are A in, B in, and we don't know whether to call it carry in or borrow in. We'll call it carry in. It can be borrow in the case of subtraction and carry in for the case of addition, but we have to give it some name, so we'll call it carry in, right? And again, result, we'll call it result out. Okay, and we'll also call it C out. And one more input that is going to come is add or subtract. So here, it'll output will be if add or sub equals 0, then it will produce this carry out, and and result out will be the sum of the three input bits. Whereas if add or sub equals 1, then it's a difference. Okay. So you have the choice of again going back to the drawing room and drawing board and sort of redesign. Okay. See, one thing you may have realized, in full adder and subtractor, the output is the result out is always a XOR, right? It doesn't matter. So result out is always the XOR of the three inputs, right? So we can say A in XOR B in XOR C in, because in both the cases it is the, so we can say assign result out, whereas the carry out was different in the two cases, right? I think in one case it is AB plus BC plus CA, right? Whereas in the case of the subtractor, it was A bar B plus A bar. So it's A bar B and A bar borrow and B and borrow. Okay, so it's slightly different in the two cases. So we'll have to say something like, if it is add or subtract bar, that means addition, then the output is A in B in or B in C in or A in C in. Okay. So if this signal is zero, then this is what the output is. Or if this signal is one, then the output is A in bar. We have to use this one. Add in, sorry, A in and it with B in, or with let us look at this output again. So A in B in, A in bar B in, A in bar C in, or B in C. Okay. So let us take a leap of faith and assume that this is correct logic. Anyway, we are verifying, right? So it's okay if we have bugs. We can always come back and figure it out. Let us assume that this is correct. And the 4-bit adder subtractor will be similar. So this will be adder subtractor 4-bit. Okay. And again, the only other difference is there is an adder subtract signal. Okay. And I think I forgot to declare these inputs and outputs. So input A in, B in, C in, add or sub, and output result out, C out. Okay. Here also X and Y are inputs 4-bit, R in is input. Uh, Here we are calling it D, maybe we can call it result, and this is C out. So let us call this C in and result out. Okay. So the adder subtractor 4-bit also has X, Y, adder sub, C in, result, and C out. So instead of full subtractor here, we'll have to write full adder subtract. So that has to change everywhere. See, sometimes all this cut paste also results in a lot of bugs. So here we can call it FAS, full adder subtractor, full adder subtractor, full adder subtractor, full adder subtractor. This part is okay. Instead of R in, it is C in. Temp 1 is okay, and this should be result. And temp 1 is okay, this should be result. Result. This should be result. Just make sure that and this should be C out. Okay. So this is a 4-bit adder subtractor. Am I doing it right? Anybody has any noticed any problems? Second and fourth instances have a extra R subtractor. Ah, you're right. See, you can compile now also. Okay, if you find errors, it'll even before writing the test bench, you are welcome to compile. So there is an error at line number 2. Invalid variable list in port declaration. Input A in, B in, comma is missing. Okay. Alright. Then there are some more errors. 17, there is an error. Full adder subtractor. Okay, this is a capital A. See, if you use a better editor, see these editors that they provide are not that great. But if you use a better editor, it will not allow such errors to occur. Then 18, 1, 2, oh, I forgot the add subtract itself. Add or sub. Okay, that happens afterwards, right? Add or sub. And this editor also seems to have its own mind and it tries to align things. Okay. So hopefully now these are all okay. I think add or sub we have forgotten. And input add or sub. Good. So it is okay now. Okay. So now we have to write a test bench. Okay. So in this EDA playground, they show two sides. One is for design, the other is for test bench. Okay. That's a good practice, right? We should not combine the test bench with the design. Okay. The test bench is meant for simulation, whereas the design is meant for later you may go and do synthesis, etc. So you should not add test bench and design in the same file. Okay. So this is a better thing. Okay. So here we can write module. Um, Ideally, we should first test the full ladder. Okay, because there may be bug here also. But right now, I'll try to directly write a test bench for add, subtract, test. So what are the inputs? There is a reg, which is, let us say, 3:0 of x and y. Reg c in, then reg add, subtract, control, then wire 3:0 some result or whatever, and wire C out. Okay. And we'll instantiate adder, subtractor, 4-bit AS4, and x and y are inputs, Cin is another input, add sub is another input, result is another input, and result is an output, and cout is another output. So we have instantiated the 4-bit circuit. And then we can do initial. See here, we can try, instead of exhaustive testing, let us try some random tests. That means we'll try some random values as xy, and we'll see. Right? We don't have to exhaustively cover everything. Let us try that. So here we'll say integer I, for I equal to 0, and we'll declare number of tests. So this is a, like in C language you may have done hash define. Here also you can write num test as whatever. Let us apply some 10 tests. So here, to generate a random number, right? There are many ways. I mean, in we'll later learn other ways also. One simple way is you could use dollar random. Okay, so dollar random is available in Verilog, but dollar random is supposed to return a 32-bit number. Okay, whereas we need only 4-bit numbers. So if you get dollar random and assign it to x and y, etc., then the last 4 bits may not be so random. Okay. So there is a little bit of a loss in that random behavior. Okay. So there is another way, right, which is called we'll write x equal to dollar u random range. So this is another built-in function. Okay. Here you can say I want a number in the range 0 to 15. Y is dollar u random range, and C in is dollar u random range 0 to 1. So we have applied all the inputs, and also add subtractor we have to do. Add sub. Okay. Then we'll supply, we'll wait for 1 unit of time, and then display if add sub equal to 0, that means we are trying to do addition. Then we'll say dollar display percentage b plus percentage d plus percentage d equals um, percentage d computed versus percentage d expected. Okay. So the we have to display x here, y and c in. Then the result that we computed is called result, and the expected result will be a plus x plus y plus c. Else dollar display percentage d minus percentage d minus percentage d equals percentage d computed and expected. X y c in and result, right? And then x minus y minus c. Okay. So we are applying some 10 tests, and if it is 0 we are displaying plus plus, and if it is add subtract is 1 we are displaying minus minus. So see whether this provides anything. So we are taking a lot of risk here. 18 there is some problem. So in 9 plus 4 was 13, 8 plus 12 was 8 plus 12 cannot be 4 here. But borrow, so C out we have forgotten. Na? Sorry. So again we have made that mistake. See, the computed answer should also be 16 times C out plus result, right? And plus y plus c. See, this is what I don't understand here. Why it should show is this as 4. There is 8 plus 4, 8 plus 12, 20 to show, no? Same thing I think here. We have to write a separate integer. Okay, and here we have to write begin expected result equals x plus y plus c, and here we'll write expected result. Whereas if it is else begin expected result is minus 16 times uh, C out, right? Plus x minus 16 times this one. No, here we are simply saying x minus y minus c. Okay. Okay. So let us see if this corrects the problem. Okay, now there is still a problem. 4 plus 9 is 13, right? Computed cannot be 27. So that means there is some bug in our. So we have to suspect this guy. Maybe the full ladder has some problem. We have to check this out. In some cases it is failing. Can you see 8 minus 8? This is minus 1. So signed, okay, signed we have to write. No? We forgot the signed part. See, this is wrong. 4 plus 9 is wrong. So just check this out. What mistake we may have made. A in B in and C in is the XOR gate. Here, if add subtract is 0, then we are doing A in B in plus. This is correct, no? Strangely, it is failing in addition, not in subtraction. What is the error? So at least as verification engineers, we should make sure that we are not, see, this is the designer's problem. Okay, as verification engineers, we should make sure that we are not pointing false alarms. Okay, we should make sure that it's minus 60. If add subtract is 0, then the expected result is x plus y plus c. Otherwise, the expected result is x minus y minus c. And we are displaying x, y, c in 16 times your plus result, expected result. So this guy has gone wrong. 15 plus 12 plus 1, the answer is 28. But I am getting 3. So they are also wrong. So my add subtractor, there is some problem. Result out is A in XOR B in XOR C in. It was just to be on the safe side. Let us go ahead and add these parentheses. I don't think that is a bug. I'm not checking at the. Oh, you know what? That could be the problem. This whole thing could be. I have to put a parenthesis here, right? And then this also should be a big parenthesis here. In if it is true, then A in bar B in. Here also let me put parenthesis. Here also let me put parenthesis. And here also let me put parenthesis. Okay. This is still wrong. Surprisingly, the adder is giving wrong answers. No, subtract also gives wrong answers. Let us do one thing. Always at A in, B in, C in, add or sub. If add or sub is true, then assign result out, C out to A in minus B in minus C in. Else result out, C out equals A in plus B in plus C. So this is behavioral code. There is some bug here. Let us see whether this will fix the problem. Oh, this has to be range, right? Are we sending the inputs in the right order? Uh, X, Y, C in add or sub. Order seems okay, right? X, Y, C in add or sub. And the outputs are resultant and 1. That seems okay. So what could be wrong? Anybody is. So the numbers we have considered are out of range for the 4-bit sign. Oh, is that true? Why, man? They're all 4-bit numbers only, isn't it? 8 and 12, etc. That's not the. I have given range, no? U random range I have given. So they are well within the range. See, including the carry, see, remember how I'm calculating the output, okay? I'm saying 16 times C out plus result. So I'm taking the carry into account. If you are worried that when I add 8 and 12, it exceeds the 4-bit range, that is factored in the carry. Okay, so that is not the problem. So who will tell me what the problem is? Okay. The input A in B in C in add or sub, output range result out, etc. Always at C in B in C in add or sub. If add or sub, result out C out equal to A. Okay, or seems okay to me. Any connection errors? Uh, 3 colon 0 xy C in. So here I have written xy add or sub C in. I don't know how I'm sending it there. See, maybe that is a mistake. In my instantiation, see here this is an error. XY C in adds up. Whereas here I have interchanged those two. Okay. See, add or sub should be first, then C. Mhm. There may be more such bugs. Okay, there may be more such bugs. XY adds up the in results out. I have declared X and Y as register 0, 3, register, wire 3 colon 0, wire C colon 2. X is. See, notice that the subtraction is okay. Okay, subtraction seems okay here also, right? The adds are going wrong. Let me just make it always subtraction. Even subtraction, there are some errors. Anybody found any errors? Line 18. Line 18, somebody is saying a problem. Line 18. If adds are big, oh, what is the error? Here, huh? Result. Absolutely correct, man. This is wrong. This is very good. Correct. That was the bug. Very good. Carry is the between the result and carry should be result out. That's correct. See, now it's okay. Okay. So we learned something. What is the learning for us in this? Okay. That was fantastic. Who found this error? Nirmala. Very good. Nirmala. You found the correct problem. And I think Jain also did it. Very good. Good debuggers. Okay. Good. So I hope everybody appreciated what they did. They figured out that when I add 3 bits, the carry has the higher, you know. So if you treat the sum as a 2-bit number, it should be carry out followed by result out, not the other way around. So when we do things in a hurry, all these things occur, right? So I hope the other learning for you is the how you can do random testing. Okay? See, even random testing brought out a lot of errors. Okay? We can increase the number of tests. And once again, we can do equal to, and see, it will be a lot of output. I don't want to compare everything. So you can do exactly what we did earlier, right? And compare the expected result with this guy. Okay. So you can say if they are the same, then don't do anything, otherwise display. Okay. If 16 times C out plus result is not equal to expected result, then only display. Similarly here. So only if there is an error, show. So no errors came. So that means all the tests passed. Okay. So we can, in this example also, there are about 512 cases. So out of that, we have sampled 650 test cases. So see, when we do the testing, here, what are the things we should exercise, right? Can anybody tell me what all we should be confident of? Okay. We may be worried that some tests will never happen. See, for example, suppose our tests were such that only additions were done. That is called coverage. The functional coverage of this test bench, we should be confident that look, both addition and subtraction happened, number one. We should be confident that carry output was one in some of these cases, right? And we should be confident that carry input was both 0 and 1, right? So there are some of these aspects that we need to worry about, right? Otherwise, what could be happening is it did not cover all the corners. Okay, some things were left untested. By increasing this number, maybe we will, suppose we say 60 or 75. So then, who knows? It may uncover some bug, right? For all you know, I think we fixed all the bugs. Okay. But who knows, there may be some lurking bug which we still haven't fixed. Okay. We had, what were the errors we found? Some incorrect connections. Okay. Connections are wrong. And this carry and result we had interchanged. Okay. So the point is, if the designer has, see, designer also will test. Okay. The designer also would have tested this thing, right, with some test cases. Okay. But maybe he still could not figure out, some of those tests did not bring out this problem. You may have noticed that even when the bug was there, some outputs were matching actually, isn't it? Even when there was a bug, some even a buggy hardware will produce correct results in some cases. Okay. And by looking at that, if we were very unlucky, we look at all those cases and conclude that it works. Okay. And in the verification it fails. Okay. So that was what the learning was. Is that clear to everybody, what we learned out of this? Okay. So you have to have a sharp eye for all this debugging, etc. Okay. So I'm very impressed that some of you found out all those problems. Fantastic. Fantastic. Very good. So let me send you the table. For all this may be okay. Now we can go and This, I don't think there is anything wrong with this. Okay, so we can. I think we are not doing anything wrong here. Okay, we can. I will request you to fix the assign statement and see whether there was any bug. I hope you got all the code. Sometimes it doesn't send everything. See, it's truncating. I think no. No, it is truncating. So I'll only send the module full adder subtractor. So this is full. Then I'll send you this subtractor 4-bit, and the test bench. Did the test bench reach fully? I don't know. Sometimes it truncates. I think it would have reached because it's not such a big one. So please look at the last three files which I sent. Okay, one of them is a test bench. The other is the full ladder subtractor and the 4-bit full ladder subtractor. So for Professor Vinith Savula, maybe I should put them in some file because he likes to put it in some Canva something. So let me put a notepad. So this is the test bench. Then we have the design. So please, whenever you can, do not mix the design and the test bench. Okay, then you'll have problems. All right, I will send this to Professor Vinith Sahula separately. Any other questions? Anybody? Any you want to discuss anything? Something was not clear. Okay, so looks like things are clear. All right, so let me pose another problem to you, right? So imagine that we have a uh, microprocessor which has 8 interrupts. So there is some processor, okay, and there are 8 possible interrupts. There are 8 of these. I'm too lazy to draw all of them. and it produces. See, these are interrupt inputs. Okay, there are 8 devices which may be looking for interrupt for the processor, and let us assume that the this guy has the highest priority. So if this guy interrupts, the interrupt will be acknowledged. Okay? And if this guy is not interrupting, and then this guy is interrupting, this guy will be taken. Okay. So if none of the previous ones are interrupting and this last guy interrupts, then he will be acknowledged. I hope that thing was clear to everybody. Is it clear? And the output I want is actually only, I want you to tell me which processor's interrupt should be acknowledged. Okay. And they should be, it should be a number, like I'll show you. Hey, this color is so terrible. Okay. So let us, the inputs are interrupt requests from 8 devices. Okay. So these are labeled, let us say we call it IRQ7, IRQ6, IRQ0. Okay. And the output is the ID of the device whose interrupt is acknowledged. See, for example, and we are using priority. That means highest priority to IRQ7. Okay, least priority IRQ0. So if the inputs are, let us say, 00110101, okay, this means I 7 and 6 are not interrupting. 5 is interrupting. Okay, so it will get priority. So output will be 101. Okay. Everybody understood this? So you, very important to understand the problem. Okay. If we don't understand the spec correctly, our design will not be correct. So here there can be misinterpretation as to, which one has higher priority. Is it 0 or 7? Right. So here I am telling you that 7 has highest priority and IRQ0 has the least priority. So I hope there is no misinterpretation possible. So how do we design something like this? See, Carnot is out of question. Okay, you have 8 inputs. Okay, so there is no way you can draw Carnot maps of 8 inputs. because that will have too many things, 256 inputs, etc. So you can't design it with Kano maps. So how do you design this? Any thoughts? I'll give you a few minutes to think, okay? So take the next few minutes to think, and if you want, get yourself some tea or whatever. Gate zero. Gate zero. I should give you a paper, you bring it. I should do something there. You will get. You get. Yeah, people are giving different answers. Some people are saying we can use behavioral modeling. Then they're saying KSX can be used. PPT not visible, no? So you're absolutely right. It's a priority encoder. Okay, that's correct. So give it a try. How would you design this? Oh, my screen itself is not visible. I see. I think my screen is shared. Is it visible now or what? See, when I see the chat, you cannot see my PPT. But otherwise, I think I am sharing the screen. So people are giving different solutions, right? Yes, you can do it that way with KSX, etc. So let us try writing that module. Module priority encoder. And let us say it has 8 inputs. Okay. which were called maybe IRQ, and the output is interrupt device ID. Which device or which interrupt is being recognized. So this is out. So sometimes it is useful to say define num interrupts is 8, and then you can say input num interrupts -1 to 0 IRQ. See, this way tomorrow if you want to change it to some other value, you can go ahead and change it. Similarly, what about output? How many outputs should be there? If I have 8 inputs, what is the number of outputs? Yes. So you can also, what will be the number of outputs? Anybody wants to tell me? If it's 8, then there will be a 3 input thing. So how do you write 3 as a function of 8? It's a logarithm, right? So you can say code define uh, ID length or ID size. See, there is a function called C log 2. C log 2 means ceiling of logarithm to the base 2. Okay. So when you take log to the base 2 of some number, if it is not an integer, you can round it off to the next higher number. So that is what we are doing, and the output is ID size -1 to 0. Okay. So this is one way of doing things. Another way is you can treat it as a parameter. You can say I have a parameter called num interrupts. So this is not required in that case. And here you don't need to say backquote. This is a parameter. So you choose whichever you want. And here you can say $C log 2. So here I am making a module which has a parameter called num interrupts. And it has these inputs and outputs. That clear? Not audible. Priyanka to everyone, not audible. What is 3? Okay. Number of interrupts is 8. Yeah. So the default value is 8. That's what you are saying. Yeah. So the default value can be given here when you declare the parameters, right? Correct. So now many of you have suggested things like, we can use case. Yes, you are right. So here we can say always, whenever the inputs change, that is when the interrupts change, then we have to go from the highest to lowest or something like that. Okay, or we can go from lowest to highest. See, there is a case where the inputs are all zero. That means nobody is interrupted. Then I think we should produce an output. It's not clear, right? See, this is what I meant by spec. Okay, the spec doesn't say anything about what should be the output when none of the inputs is one. Okay, so we can assume that in that case, ideally we should give one more output saying nobody is interrupted. So is anybody interrupting? Okay. So if nobody is interrupting, then we should make this false. That may be the easiest to calculate. If the input is all zeros, then is interrupt is false. Otherwise, it is true. So it is nothing but the OR, isn't it? So if I take the OR of all the incoming requests, if all of them are zero, then is interrupt will also be zero. So we could use assign for that. Assign is interrupt out. You are allowed to do this. See, if you say or and within bracket this wire, this is a there's a bunch of wires here, so it will take an or of all of them. You don't have to say IRQ in 0 or with IRQ in 1. So this is a clever way when we don't know how many inputs are there, etc. You can't write IRQ in 0, etc. because you don't know how many are there, right? So this is available in Verilog to say, just take the R of all the inputs. Now the other case is when one of them is actually interrupting. then maybe we can go from 0 to higher. So we can declare an integer called I, and we can go from I equal to 0, I less than num interrupts, I equals I plus 1. So we'll keep checking. And if IRQ in of I is true, then ID is equal to is I. So it's a behavioral model. Okay, it'll let us assume that both 0 and 7 are interrupting. Okay, so in the beginning it'll check the ID to be 0, but when we go to 7, if it is high, then it will change it to 7. So this is one way. Any doubts? Anybody has any comments? ZZ should be the output if no interrupt is there. No, why? You should not do that. See, you should not tri-state the outputs if there is no interrupt. That's not correct. Can we default acknowledge ID? No, no. Default acknowledge ID out should not be 0 because 0 is a valid device. See, if nobody is interrupting, we should not say 0 is interrupted. That's not correct. What is valid? Agile Matthew. If multiple agile Matthew, if there are multiple interrupts, it will take the highest one. That priority is happening, no? See, it will start from 0. If 0 is interrupting, it will assume that the acknowledge is it will give the acknowledgement to 0. But when it goes to, let us say, 5, if that is also 1, then it will change it to 5. So at the end, it will give the priority to the highest ID. That clear to you? Agile Matthew. Default use for all zeros within case X or case Z. In this case, because I am using parameterized, I may not be able to use case X and case Z. So this is a one way of modeling. If the number is 8 always, then of course I can change. I can write a case statement and write down the all the possible cases. Okay. Case X means when one of some when we care about, let us say, one of the, let us say we are interested in whether IRQ7 has interrupted. If IRQ7 is 1, the others are don't care. Okay. If the priority, if highest priority device is interrupted, then it doesn't matter what the others are. So that is why we say it is don't care. Okay. So case X is actually a good way of doing it if we know exactly 8 priority interrupts are there. Now, how do I verify this? We could do the same thing like our earlier. So we could go and put this here. Make sure that it compiles correctly. 8 is some syntax. Semicolon was missing. Okay, and 13. Act ID out. Oh, okay, okay. This is a register. So because we are assigning here, we have to declare it as a register. That's right. Correct. Oh. Now, how do we write the test bench? Priority encoder. Here also you can try the same thing, the randomized tests. So first thing is to bring a copy of priority encode. See, if you want to only keep it as 8 bits, then you can leave it as it is. But if you want to test for the 4-bit case, you can say 4. Then give a name, let us say instance of priority encoder. Or we can declare num interrupts to be 4 and make this also num. Okay. I have declared 4 and we will need registers as many as the number of interrupts, and these are our IRQ, and we'll need a wire which is so here ID length minus 1 to 0 of ID of the interrupted processor, the acknowledged processor. Then one more wire for that no is interrupt out, is interrupted. And here we'll send all the inputs. The first input is the IRQ. The second thing is the I is interrupted. And the third thing is ID. So this completes my hardware. Then I have to use the initial statement to sort of put some data. Okay. So we can declare an integer I and we can declare some tests. See, with 4 inputs, there can only be 16 cases. So let me take some 10, I think. So we could have done exhaustive. So IRQ is your random range. It can go from 0 to 50. See, this is where the thing is. See, among these 10, will the case 0 come or not? We don't know. If 0 doesn't come, then our testing is incomplete. When we rely on random testing, that is the danger we have. Okay. Then wait for 1 unit. Oh, I forgot the for loop, right? For I equal to 0, I less than num tests, I equals I plus 1. Then write the device. Interrupts equal to, let us write percentage B, right? And then let us write output is acknowledged, what is it? Interrupted equals B, acknowledge ID equals D. So IRQ is my pattern, then is interrupted is here, and acknowledge ID is ID. And there should be a for and this is the end of for, this is the end of initial. Okay. So see whether this works. So in this case, both of them were interrupting. So 3 was given the priority. Then 2 was given the priority. There was only 2. So you can see that the case of 0 did come. And see, acknowledge ID is 1 because in the previous cycle it was there. So it continues to be here. But we assume that the user will look at this and take action. Okay. So here acknowledge ID is 1. Okay, because the previous case was it's a registered output. Okay, acknowledge ID is a registered output. So as a result, whatever value we had put in the previous simulation, that will remain. Okay. So I think it is acting as a. So now you can try increasing the. Suppose we have number of interrupts is 16. So we have 16 processes. I'm sorry, 16 interrupts. Okay. And then we can try the same number of tests. So you can see that now we have given priority to 3. Okay. There is something suspicious here. Why is it that none of these guys, or is it because we have to increase? Something is wrong. See, only the 4 bits are. Have I made some mistake somewhere? Oh, here. This 15 is coming, right? That is all. So we should make it 2 to the power n. Okay. So that was an error. Okay, now you can see these that's around. So here 15, then 13. So I think the logic is okay. Any doubts? No, in the design, we don't have to do anything, man. See, here we don't have to do anything. See, this we don't have to change it to 16. Okay. Only this has to change. See, that is the beauty. Okay. This is, I can make it 32. Okay. And you will see that it will still work. I think 32, what happens is 2 to the power 32 unfortunately is 0, right? So it won't work. See, this U random range will fail. So we can try 24. Okay. So 24 is okay. We don't have to change this to 24. Somebody asked that question. Akash, even if a higher priority interrupt is found, the loop continues and might override. No, it is supposed to, it should continue, man. Uh, Om, Om Nayak. See, we are going from lower priority to higher. See, the loop here, it starts from 0. 0 has the least priority. So we are starting from least priority to higher. So we want the higher to overwrite. Okay, we are not going the other way around. Is that clear to you, Om? Okay. Required means, sir is required means. Yes, yes. I think he wants to know whether this backcourt is required. You must put that when you are doing hash define. Okay. I think his question is this backcourt is required. Yes, it is required. In parameter, we don't put. See, if it's a parameter, we don't do. But if it is a macro definition, we have to put backcourt. Okay. What else? Sir, first line. What is first line, man? Yeah. What is the first line? What is the question? Agile. I don't know what is your question. First line means what? Anybody else this chat I missed? I can only see some things here. I don't know. There is a button here. Okay, so one more end is required. Yeah, good. All right. You can also try to design this for a specific case of 8. Okay, can anybody design this for the case of 8 and tell me how it will work? See, for a generic case, I agree it's not easy. But for a specific case of 8 or 16 or something, we should be able to design it. How do you design it? How do you generate these outputs? See, what we could do is just a second. Somebody said, See, we can first generate interrupt acknowledge, okay, for all the guys. Okay. So imagine that I first generate interrupt acknowledge. So these are the requests and these are the acknowledges, right? So how do you acknowledge for the zeroth guy? I'm sorry, seventh guy will always be acknowledging. If this is high, this will be. So this is same as IRQ. IRQ, I acknowledge 6 will be, if 7 is not acknowledging, he will be. Okay, so I'll show you the logic. So I acknowledge of j equals, if anybody, the higher priorities are not acknowledged. So IRQ, um, IRQ n minus 1. I don't know how to write it, man. It's very difficult. See, let me write it with suppose this is IRQ. So I acknowledge 7 is same as IRQ 7 because if 7 asks, he gets. Whereas this one will be if 7 is not asking. If IRQ 7 is not asking and 6 is asking. The last one will be IRQ for the 7th guy. I'm sorry. Um, if 7 is not asking and if 6 is not asking and so on, and if neither 1 is also not asking, and last IRQ 0 is asking, then this guy will get. Okay, so these are the acknowledges. Okay, so these are fully decoded. Okay, now we have to generate this by encoding. Okay, how do you encode? When will this be 1? See, if any odd guy is any odd numbered ones are high, then so basically it is I acknowledge 3. I'm sorry, I acknowledge 1 ORed with I acknowledge 3, or I acknowledge 5, or I acknowledge 7. Correct, no? So then this bit will be 1, because in 1, 3, 5, and 9, the least significant bit is 1. Similarly, which numbers have 1 in the second bit position? So 2 will be one of them, 3 will be the other, then 6 and 7. So 2, 3, 6, 7, we can OR them. Then last one is I think 4, 5, 6, 7. So if 4 is asking, 5 is asking, 6 is asking, and 7 is asking. In these 4 cases, the device ID will be okay. So we can try that also. We can do it fairly easily for an 8-bit case, but to do this in general may be a little bit tough, or may not be so difficult. So what we can do here is, let me first give you this. So I will give it to Professor Sahula. No point in exercise 2, priority encoder. So we'll keep some wires, as many as num interrupts IAC. So these are the same wires which I showed earlier. Okay. So these wires. Then this is okay. The this is fine. Here, what we can do is, instead of this always with the way we are doing it, I'm not sure whether we can write it without. Maybe we can try. For I equal to 0, I'm sorry, I equal to 7, I greater than or equal to 0, I equals I minus 1. I act 0, I of I is there a way to do this? We have to take IRQ in 7 colon I or I minus 1. Get I minus 1. See, for the case of I equal to 7, now we have to say I plus 1 maybe. No? See, let us take the case of 5. So 6 and 7 should not be interrupted. Okay. So we can possibly write suppose we do this. What we are saying is look at I plus 1 up to 7, or in this example not 7, it should be num interrupts minus 1. Okay, so go from I plus 1 and check if any one of them are and the or of those, if it is 0, that means nobody is interrupting. Anybody higher than me is not interrupting. Then this not will give me a 1, right? Then I can AND it with IRQ of I. So I believe this is how we generate the IAC. This should not be 7. It should be num interrupts minus 1. Is that okay? Did you guys understand? Okay. A lot of answers have come. Very good. Very impressed. Now we have to encode. So once we do this, we have to encode. And how do I do that? We have to go from I equal to this C log 2, etc. We can start with 0, I less than this, I equals I plus. So we have to find all those values of numbers in the range 0 to num interrupts minus 1, which have 1 in this position I. How do I do that? So what we could try is we could write another output, another reg temp. So we'll which has a similar size. So we'll say temp equals I, and no, temp is not I. Temp is okay. Maybe we have to write another for j equals 0 j less than num interrupts j equals j plus 1. Okay. And if so we can write temp equal to j, and if temp of I equals 1, right, then hack id out equals 1. So initially maybe we can set hack id out equal to 0. Let us see. What we are doing is initially we generated the acknowledge signals. Then for each of those ID, okay, this ID, initially we'll set that to be 0, that bit to be 0. Then we are cycling through all the J's, J going from 0 to number of interrupts. And I'll copy that value of J into a temp, which is declared as a register here. Okay. And if the temp of I happens to be 1, then that means we have to take it. I hope this will work. J is not declared. Huh? Syntax error. Num interrupts. Anybody caught the error? What is the error? So 16 there is an error. Okay, we have not declared IAC. Huh? We have declared no IAC. Oh, it should be registers. Yeah, yeah, sorry. Should be IRQ in. 16 module instantiation. IRQ in. What did I do? maybe one more. Oh, you know what? Always I forgot. No, always at hierarchy. Priority included. Oh, okay, okay. You know what? I wanted to copy this for your case, but I don't need to do it. Oh, it's not allowed. Huh? Sorry, guys, it's not allowed. See, I was trying to access all the higher elements, but looks like that's not a reference to wire or register high is not allowed. My apologies. This is not allowed. It's if we had a fixed value of second for loop should not be used instead for other letter. See, this I plus one is causing the problem. A reference to a wire or edge is not allowed in a constant expression. Really, you can't do this. Okay, we'll do one thing. We'll do we'll do it sequentially. We'll declare a wire or a register card is higher interrupt. So we can set that to higher interrupt is false. And then for j equal to I plus 1, j less than num interrupts, j equals j plus 1. Higher interrupt equals higher interrupt ANDed with the IRQ of J. Okay. Then this guy is higher interrupt. Okay. Let me explain this. Okay. What we are saying is, since it doesn't allow me to select IRQ with I plus 1, etc. So for each of the interrupts, I will keep one variable called higher interrupt, and I'll go from I plus 1 all the way up to the highest number of interrupts, and I'll basically calculate this should be not, I think, no? If the previous guy is not interrupting. Okay. So higher interrupt is initially 1. So for example, if let us say I is equal to 5, okay, then what we are doing is we are going from 6 onwards up to uh, 6 and 7. So higher interrupt will be initially 1, then it will the next it will become not of IRQ 6, and then again it will become not of IRQ 7. Okay, and then finally not interrupt. If higher interrupt is not coming, and I have interrupted, then I hope this will work. Nineteen. Okay, higher interrupt is not there. Higher interrupt is there now. Double R. IRQ in. I think. No, no, sorry, this is wrong. There is some bug here. For I equal to number interrupts minus 1, higher interrupt is 1. We go from j equal to I plus 1 and all the way up to number interrupts. And we take, I think this should not be not. Wait, wait. It should be or, I think. If any one of them is interrupting, it's higher interrupt. So, if higher interrupt, if none of them are interrupting, right? So I think not was correct. No, if none of them are interrupting, okay, this was. Ajay? No, wait, wait. Okay, maybe the errors are here. Okay, the problem is here then. See, you are allowed to see the I, what is it? IAC, right? Let us verify that IACs are correct. So what you have to do is the instance priority encoder dot IAC. Okay. So you have to give the instance name and then say dot IAC. Then it will display that guy also. So let us do one thing for the sake of this. Let us not keep it 24. Let us keep it 8. The acknowledges are probably correct. No, see, the one means one, second one. See, acknowledges are okay. So the problem is this part is okay. I think the problem is here. For I equal to 0, IAC OIT out equal to 0. Oh, you know what? I think this should be IAC I, no? This I itself is missing. I don't know how it didn't point it out. No. Can anybody see the error? We are going through all the in this case there will be three times. I will go from 0 to 2. Initially, ID that zeroth bit will be set to 0, and then I'm going through all the acknowledges. Hey, wait a minute. I'm not even using the acknowledge here. No, that's a mistake. The ISCK is calculated here, but it's never used here. How do I use it? Oh, so IAC 3, etc. I have to do, right? That's the mistake I have done. I think I had to say IAC J. This J is okay. What is this here? IAC 2367. So I have to select 2367. So this is something tricky. Let us see if anybody has cracked it. Uh, Line 16 begin is needed now. Is there no? Here is a bug, man. See, I have calculated the acknowledges. Then the zeroth bit of this should be, I should sample the IAX if that bit is zero. Too tired to think. See, now this is correct, I think, right? 7, 6. It's okay. I think now it's okay. For some reason, all these guys are always interrupting. So 15, 14, 13. So we are never giving a chance to these lower guys. Now here we have a 10. So now it's okay. Okay. So again, let me explain this. Okay. There are 6 minutes left. So we should be able to help. What did I do? I am doing exactly the way I explained it here. First, I am doing the acknowledges. Okay. How? Let me put a comment. First, calculate the interrupt acknowledge signals. So what I'm doing is for each interrupt, okay, from zero, I'm starting from the last one going all the way to zero. Higher interrupt equal to the higher interrupt signal tells me if people above me are interrupting. Okay. If I am I or I plus one, etc., interrupting me. So I have to go from I plus and I plus one, right, and check if anybody higher than me is interrupting. So if any one of the IRQs are interrupting, okay, so when I come out, if anybody above me is not interrupting me and I am interrupting, then that will be my acknowledgement. That clear? So this is to check whether the interrupt acknowledges. Then I'm going through this loop to calculate to do the encoding. Initially, that there are these many bits to be encoded. I'll start with 0, and then I'll go through all the um, n values 0 to n minus 1, where n is the number of interrupts. Okay, and then if as I explained to you earlier, right? See, when I'm calculating this bit 0, I'll go through 0, 1, 2, 3 up to 7, and I'll check whether in the position 0 1 is there or not. That is what is happening here. If there is a 1 in that position, if yes, then the corresponding acknowledged value will be OR together. Okay, so remember that is what we were doing here, the OR of all those four signals. I hope this is clear, but if it's not clear, I'll explain it to you tomorrow, next time, tomorrow when I join. Okay. How many of you understood this logic? I'm curious. So they is saying, yeah, if the higher interrupts are 0, that is, it is taken into account. I'll explain it to you tomorrow. If any higher interrupt is active, yes, it should block the current one. So the current interrupt should be active only if previous are all 0. Okay. That's what I'm doing here. If all the previous ones are 0, okay, not of IRQ in J, for J going from I plus 1 to the last number, then the higher interrupt is not there. Maybe it should say higher interrupt not there or something like that. Okay. Maybe this higher interrupt is 1 is maybe confusing. Maybe I should reword it as nobody higher is interrupting. If nobody higher that may be, that's a good point, man. Higher interrupt not present. Okay. We'll change that tomorrow. Okay. The variable name is confusing. Higher interrupt, what I mean is nobody above me is interrupting. Does it make sense? Okay. If you do it for a specific case of, see, the reason it's a little complicated here is, see, Verilog doesn't allow things like if I have a register of 7 bits, I cannot say get me the values from I plus 1 to the end. It says, you need to have only constants. So that is why I'm forced to write a for loop here. Okay. All right. So I will send this also to you. The test module didn't change. The test module is the same, but I will still give it to Professor Vineet Sahula, and you can take it from him. Okay. All right. So think about it. Okay, and I will send this to you, by mail, and tomorrow we can discuss it again. Any questions? Everybody is following? Are you guys following? Yes. Good. Very good. So tomorrow I'll explain it again. Okay. I think in the end there's a little bit of cloudiness. So tomorrow we'll explain. All right, guys. See you. Good night. Tomorrow we'll meet at the same time. Bye
Thank you, sir. Good.
bye.